Okay, so today we have in our seminar, in our online seminar, Pawel Wolff from CNRS France, and he's going to talk to us about a joint work with Franck Barthe on volumic properties of high-dimensional Orlicz balls. So whenever you want.
Okay, so thank you very much for invitation. It's even I'm not physically in Zaragoza. It's a pleasure to be here. I've been here. I was invited here as during my PhD thesis for 6 months. I worked with Jesus Bastero and Julio Bernues, and since then I've gave few talks already on this seminar, and now it's the next one. So I'm glad to be here again. So today I will talk about how to compute a volume of high-dimensional Orlicz balls. So kind of a simple problem, and let me start with the warm-up example. Let's take a ball, n-dimensional ball in LP sequence space. The unit ball is like you see here, and one can compute the volume exactly with the exact formula, and if one wishes to, one can provide a more compact formula in N, which via Stirling's formula to provide an approximation with some relative error, 1 plus big O of 1 over N. We would like to be able to calculate the volume of more general convex bodies, not a very general one, but let's enlarge the class by so-called Orlicz balls. Okay, so here let me recall what it is. Namely, for let's take psi to be a Young function, which is just a convex function with which vanishes at 0, and it has values in R+. It's not necessarily symmetric, and we define an Orlicz ball in Rn, n-dimensional Orlicz ball generated by the Young function as the following set. It can be proved that this is a convex set, not necessarily symmetric, if psi is not an even function, and taking the absolute value to the power p as our Young function, we get back to our previous example. So our aim will be to find the formula that provides asymptotic for the volume of such an Orlicz ball. And actually we will, since we want to have this formula asymptotic, we need to define somewhat a sequence of convex bodies of Orlicz balls. The sequence will be indexed by the dimension, but we will stick to a sequence which is generated by a priori fixed Young function, but there will be some normalization going on. Namely, essentially there will be a single a fixed Young function, but normalized somehow. So explicitly we will be looking for this convex body in Rn, where En is the level set that we are dealing with. So we will be interested in the volume of such a convex body as the dimension goes to infinity, and this level En will be of linear order in N, just to reveal what will happen, and this will actually correspond somehow both conceptually and in the method of the proof. This will correspond to the central limit theorem regime. If you have any questions, don't hesitate to interrupt. Since I cannot really see you, or it's or maybe actually I can.
You can see us and hear us, but we all have our microphones and webcams closed.
Yes. Yeah. Okay. One remark. Well, by the way, can you see my mouse pointer?
Yeah.
Yeah. Okay. This Young function is very special because of homogeneity. Also, the convex bodies defined with this Young function are homogeneous in a sense that with this rescaling operation, we get the rescaled LP balls, and this is in general not the case for a general Young function. In a sense, this way this convex body differs generally from this one, because whenever psi is not homogeneous. Okay, so let's formulate the main result. To this end, I need some notation. Let's fix some parameter lambda positive, and let's consider a probability measure on R defined in this way, where z lambda is a normalizing constant. So it's just an integral of this exponential function on R. Then let's take the mean of the function psi with respect to this measure and variance of the same function. Okay, and okay, having such a measure and two of its basic characteristics, we have all the quantities that will actually play in the formula. So the formula is here for the level set E of our Orlicz ball, which is proportional to the dimension, with proportion constant being the mean, plus the deviation from this linear term in the scale of square root of n. We have the asymptotic formula for the volume. Okay, it's quite explicit. As you see, the normalizing constant intervenes here, the level set, of course. The characteristics like the variance is there. There is a square root of the dimension in the denominator, and the term that resembles the central limit theorem. This holds for any fixed alpha. And to understand a little bit better the formula, we need to comment on error term. So the error is the relative error of this order 1 plus big O of 1 to the n to the minus 1/2. And here in this O, what is hidden are there are constants which depend on this parameter lambda, on the function psi itself, on the Young function psi, and on the alpha. And actually, this dependence is sort of regular. It's non-decreasing in alpha. So the more you deviate from the central quantity, the worse the approximation can be. So it tells basically that within the window of the roughly square root of n around something proportional to the dimension, you can for these scales you can approximate the volume of the Orlicz ball this way. Okay, so to make it a little bit more concrete, maybe you can reformulate or this result or draw a conclusion that which is the following. Now let's have the Young function psi and the parameter lambda fixed, and now we can say that actually for any bounded sequence of numbers an, we can take these levels and approximate the volume with similar kind of formula. Okay. Here you could one can write simply the same relative error as above, and the same the constants of in this error depends on lambda psi and bound for the sequence an. Okay. Okay, so let me maybe comment a little bit further on that. Here I just, at the top line, I just recalled the notation, the measure that is like a central object here, and its basic characteristic. Sorry, there should be psi of x and psi of x here. This is the mean of psi of x and the variance of psi of x, and not the mean of the measure itself. Sorry for the typo. And here's the corollary. And actually, one can ask for the role of this parameter lambda here. And it turns out that it's a simple analysis to see that actually you can do the reverse. You can fix the proportion m, the proportion in which will be the linear factor of the standing by the dimension for the levels of the Orlicz balls that for which we are looking for. And okay, here's sorry, psi missing again. And then it turns out that actually there exists lambda, which for which this m is the mean of psi of x with respect to this measure psi, with respect to this measure mu lambda. Okay, so first I presented the result in a way that okay, you fix the parameter lambda, and then you have some characteristics like this m being the mean of psi of x with respect to this measure, but you can reverse it and to fix these characteristics and to find the parameter lambda that fits, and it's always possible. So actually you can do this. You can see the result in this way, that you can consider a sequence of Orlicz balls all generated by function psi, but rescaled for the given dimension n, rescaled by this number, which is proportional to the dimension with the proportion m that you choose a priori, but you are free to choose any positive number. And then you can move freely within a window of the size square root of n, where an is a bounded sequence. And then you have the formula, approximate formula for the volume, which is like this. And you have solve for lambda, which is like, okay, it involves something like implicit equation. Any questions to the formulation of the result? Okay, if not, I will now present some. Actually, our main motivation to tackle this problem. Our motivation was came from the conjecture of Kannan-Lovasz-Simonovits, and more precisely, we wanted to understand somehow the applicability of the result of somewhat recent result of Sasha Kolesnikov and Emanuel Milman and Sasha Kolesnikov on this conjecture, where they showed the conjecture for the class of so-called generalized Orlicz balls, similar class of convex bodies, but it was somewhat more larger than the one that we are considering here in this talk. Namely, maybe let me comment. They just for every coordinate they can have a different Young function psi. So they have a sequence of function psi which is a priori infinite, and so at along each coordinate, the Young function can be different. Okay, so let me quickly maybe explain recall what the Kannan-Lovasz-Simonovits conjecture is about. So here's one of the formulations, which is via Poincare inequality for a probability measure on Rn. So this is the inequality, the functional inequality. And we want to check such inequality for suitable class of functions f, namely smooth functions or local ellipsis functions on the Rn. And what one is interested in is the optimal constant with which this inequality holds, if it holds with some finite constant. Okay, so let's denote by Poincare constant of the measure mu, the smallest constant for which this inequality holds in general, namely for all ellipsis functions on Rn. And here will be the constant that concerns only linear functions. Okay, so then obviously the constant for which concerns only linear functions is not greater than the general one, the true Poincare constant. And the conjecture of Kannan-Lovasz-Simonovits from proposed already 25 years ago. They conjecture that actually this trivial bound can be reversed up to a universal constant, which does not depend on anything. I mean, that there exists a universal constant, just a number, and the conjecture is that okay, this bound can be reversed for measures which are for probability measures which are uniform measures on a convex body. Okay, so whenever you have a convex body in Rn, whatever the dimension is, they conjecture that Poincare constant of the uniform measure on this convex body can be actually up to a universal factor can be studied by can be found by studying just Poincaré inequality for linear functionals. Okay. Okay. The conjecture is one of the central problem in the area, and okay, maybe I will not discuss it further. I just to know more. There is you can see somewhat recent monograph of David and Jesus on this conjecture and much more. Okay, so let me now state the theorem that actually the result, one of the partial results on this conjecture that was actually our motivation to this work that I'm presenting now. And here's the formulation. Well, this is somewhat simplified and formulation of the result of Sasha Kolesnikov and Emmanuel Milman. This is simplified. There are, okay, this is not so maybe precise, but it's, and definitely it is not so general as the result they had, namely, but basically it shows the essence. And so as I've said, they consider generalized Orlicz ball here. I'm restricted just to the simple ones. Okay, so let V now be a Young function, so the convex function, positive values vanishing at 0, and let's consider again similar measure, but now let's forget about this parameter lambda, which is now set to 1. Okay, so we want to scale this function, this Young function V in the domain, so that okay, this is actually the probability measure. Okay, I haven't stated that, but we want this measure to be a probability measure. So we need to take some scaling on function V to have that. And let's consider the levels that are associated with this function, with this Young function, the sequence of levels which depends on the dimension n, and these are the scalings E of our Orlicz ball, for which we will say something towards the KLS conjecture. Okay, so these levels are defined by satisfying this inequality, that the volume of Orlicz ball rescaled by this level E is at least something like that. There's factor e to the minus e here as well. Okay, so once okay, so let's define such a set, and then they say that the KLS conjecture holds for Orlicz balls generated by the function V divided by E, rescaled in that fashion, in dimension n. Okay, for each level E from this set. Okay, they studied the set because it's essential to know whether these level sets are not empty, or a priori it's not completely clear. So they showed that the set is an interval of the length at most that roughly square root of n as n goes to infinity. And well, they provided, they proved that this set is non-empty, this interval is non-empty, and at least this quantity, which, okay, here you see this mean of the v of x with respect to our measure mu, which stands as a factor by the dimension n, and well, okay, there is some additive constant one. Okay, so so what we can show using our result is the following thing. Okay, here I recall just the definition of this level sets and basic characteristics of our measure e to the probability measure e to the minus v. And from our results, we can actually get some more explicit information about the levels for which the Orlicz ball generated by V and rescaled properly satisfies the KLS conjecture. I mean the sequence of Orlicz balls. Okay, so so actually we can show using our estimate, sorry, on the volume of Orlicz ball, we can actually show that this whole interval around the mean multiplied by the dimension plus the window of the size roughly square root of n is in this interval. Okay. So, well, more precisely for n epsilon, even close to 1, you can, okay, here's the precise formulation. But the message is that, okay, around this value, which was here, this is this mean m, not only a 0.1 or something of the points within the window of the constant size are in this set, but okay, the window is actually larger, is of the size roughly square root of n, is in this level set, and which is actually the optimal result in a sense. I mean, their method deals with this set. I mean, with the confirms the KLS for Orlicz balls rescaled by levels from this set, and this set is the interval of the most length of the length which is at most square root of n. So we via our result we somewhat get the best information on or roughly the best information on this set that we can. It does not say that KLS does not hold for the Orlicz balls rescaled by other E, but just the method of the proof of the result of Kolesnikov and Millman does not provide information for concerning KLS of Orlicz balls rescaled by numbers which are not from this set. Okay, let me mention maybe briefly another application of our result, which is result on asymptotic independence of coordinates of Orlicz balls in n dimensions. So let me recall our object, which is this measure, and our rescaling levels, which are proportional to the dimension, with this mean as being the proportion, and we are moving around within the window of the size square root of n. Okay, with by means of the bounded sequence alpha n. Okay, now let's denote by xi with the superscript n the random vector which is uniformly distributed on our Orlicz ball in Rn. Okay, Then it turns out that if you look at the coordinates projections of the dimension Kn, where Kn is smaller than grows slower than square root of n, then if you look at the projection of this random vector onto Kn coordinates, then actually the distribution of this random vector is close to a product distribution, and exactly this is a product of these measures, Kn fourth product of these one-dimensional measures. Okay, these are closed in a total variation sense. Okay, as dimension grows to infinity, it's the total variation distance goes to 0. Okay, so this is not only about independence of projections onto coordinate subspaces of the fixed dimension, but actually the dimension of the subspace can grow with the ambient dimension, but not slower than square root of n. The precision of our formula allows us to go that much. And okay, was this actually the limit of the? Okay, I'm not sure now. Okay, so are there any questions so far? Okay, if not, I would like to conclude with, okay, I would like to show somewhat the main ideas and techniques that we are using. This is okay. The things that you will see here are not very original. They all goes back to classics of probability, of to Kramer, Essen, and others, and so there is nothing really new, but okay. Okay, so let's reformulate a little bit in probabilistic terms, reformulate our problem and the formula itself. So okay, we had our measure mu lambda, and this was the probability measure given by this density. And let's now denote by x a random vector, random variable on R, which is distributed according to this distribution. So now m in short, or m lambda, is just expectation of psi of x, and the same with the variance. Okay. Okay, let's take the IID copies of x, and let's take the sum here. Okay, another typo should be, of course, xi here. So we take the normalized sum of the variables phi of xi. Okay, normalized as in the central limit theorem, and we call it by Sn. Okay, so now we can write down what the volume of the Orlicz ball generated by this function psi divided by the level E is. Okay, it's simply integral in Rn of such an indicator. In the next step, what we can do is, okay, we leave the indicator as it is, and now we okay, instead of the Lebesgue measure, we'll integrate with respect to the product measure of the one-dimensional measures mu lambda. And well, we have to compensate their its density by its reciprocal, right? So all these densities that are here, these densities are multiplied n times one by the other. So you have the normalizing constant to the power n, and okay, all these exponents are here now with the reverse sign. So this term cancels simply with the density that is in this, goes with this product measure. And well, once you have this integral written like that, instead of little xi, you can just write random variables xi, and this is the same. And instead of the integral, you write expectation value. And well, we keep our indicator as it was before. Okay, so and then using the notation that, okay, using this notation for the normalized sum of the sum of psi of xi's, you can rewrite the same, the last, the previous line finally like this, with some, okay, here you will have, if you compute, we will have lambda times sigma of lambda, which we can call L, and okay, this level E by the indicator will have, because of normalizing this sum, will be now this. Okay, so one can say that calculating volume of the Orlicz ball boils down to calculating such expectation value with some, okay, relative error. The relative error we want to obtain is this, where this error, so the relative error will be, I mean, there will be a factor like 1 plus big O of 1 over square root of n. And the constant depends somehow on L and alpha, which can be traced back to all these parameters we had before. Okay, so this is very similar to what happens, for example, in Berry-Essen, classical Berry-Essen theorem, where we are, the aim is to approximate the probability, the tail probability of Sn. Okay, so you have a similar thing, but you do not have this exponential function in S, but you just have this indicator simply. Okay, just for comparison. Okay, so okay, and in this analogy is okay. Really goes further. I mean, we'll really reuse some of the methods. Okay, so let me maybe elaborate a little bit on the strategy. So, of course, by central limit theorem, we know that Sn being the normalized sum of some random variables psi of xi will be, for large n, will be close to the normal distribution. So if, okay, assuming that Sn is has exactly the normal distribution, then okay, it's just an exercise. We can just calculate more or less. We can calculate this quantity. Well, actually, we can approximate using some tight bounds, quite tight bounds on the probability distribution function of the standard Gaussian distribution. Okay, without because without this exponential, this would be just a distribution function of standard normal distribution. And we know the estimates quite exactly how it behaves in alpha. And here with this exponential term here, if Sn is just standard normal, then it's actually okay. This is an exercise where the calculation boils down to using estimates on the distribution function. Okay, but in general, well, we know only that Sn is close to do standard normal, and we want somewhat quantitatively exploit it. And but Sn itself is not nice enough, and this is the same story in Barry Sn. We want to somewhat regularize things, to apply some analytical tools. And what we'll do here is we'll replace at first Sn by the smoothed version of it. We'll smoothen Sn by the small Gaussian term. Z stands for standard normal and will be rescaled by 1/n, and it will be, of course, independent from Sn. Okay, so if we think in more in analytical terms, Sn has some distribution which is close to standard normal, and since partially for technical reasons, but also because of conceptual ones, we need to convolve it with some nice distribution, smooth one, which will regularize things. We'll see in a minute what is the reason for that exactly. Okay, so by doing that, we'll need to do two things. Okay, finally we'll boil down to calculating this expectation for Sn plus Z divided by n for this regularized version instead of Sn itself. But then we'll need to compare the two. I mean, the original one with the smoothed one. Okay, the comparison is sort of a technical step where, here this resembles somehow the same circle of ideas like in various and theorem appears more or less. It's at least the way we do that. It's Fourier analytical proof, and where we use some inequalities on characteristic functions that are in the roots of the Berriasan theorem. Okay, so let me comment maybe more on the second point. So once we already regularize Sn, what we can do? Okay, so instead of Sn, we have this, and okay, for the sake of presentation, let's deal with this expectation by introducing another random variable. This is for a reason you will see in a minute. So rewriting the things appropriately, this is the quantity we are interested in, and you can rewrite it in terms of random variable v, random variable w. Okay, now this indicator becomes just the indicator that w is non-negative. Okay, you have some term which is already fine, and here we have the exponential function. Okay, so let's rewrite it in more analytical terms. We have just the integral. Okay, because of the indicator, this is the integral on the positive half line. Sorry, and we integrate this exponential function here. I put another factor which is which is killed by this one. Okay, I made it for, and we integrate with respect to the distribution of the random variable W. Okay. Okay, and this integrand is nothing but the density of exponential distribution with this parameter L times square root of n. Okay. Okay, so actually here you see the integral of the you see we integrate over the real line the density of the exponential distribution and the density of W. W has density, it's smooth, no, there's no problem. And even more, both densities are in L2. A priori, as the density of Sn, okay, you could, Sn is actually quite nice already, because, okay, it's this was a normalized sum of psi of xi's. Xi was distributed according to this measure e to the minus psi of x. Psi was a convex function. It's actually quite nice. But what we lack there is whether the density of such Sn is square integrable. Okay. When we convolve with such a factor, then like Gaussian, whatever n is, whatever scale is for fixed n, it's in L2. And for this reason, we can apply the Parseval formula to pass to the Fourier domain and to switch both densities to characteristic functions. Okay, characteristic function of the exponential distribution is explicit, and characteristic function of this random variable W, okay, it's expressed in these simple terms via characteristic function of Sn. Okay. And now back again to, well, this step. If we were lucky that Sn is standard normal, then I said that we can just calculate whatever we need. And well, here the same story can be seen. If Sn was Gaussian, namely this characteristic function has similar form, is exponential to the minus t squared divided by 2, then we are done. Okay, because what we have, this is this integral over of the real line. We have some Gaussian, maybe this kind of term, linear term in t, quadratic term in t, quadratic exponential, and we have this Cauchy-like term. But okay, you can just compute it. You can do Parseval back if you wish. Gaussian will remain Gaussian, and linear term, and that will, okay, you will get back the exponential distribution. Okay, but in general, well, Sn is only close to Gaussian, and okay, so then we know, this is again here in this context, we also use the tool from the proof of Berry-Ascend theorem. It's sometimes called Ascendant Inequality, which quantifies how close quantifies somehow this is a core of quantifying the closeness of distribution of Sn to the standard normal distribution. Namely, it states that the characteristic function of Sn is close to the one of the Gaussian, of the characteristic function of the standard Gaussian, within a window of the size roughly square root of n, and this is the error bound. Okay, this is of the order 1 over square root of n, so it vanishes in n and it vanishes exponential. I mean, like in a Gaussian way. I mean, but this is in a finite, in a window of square root of n, right? Okay, so I'm already finished. So yeah, so this way you know how to tackle the how to quantify the deviation from the Gaussian case. So if Sn is not perfectly Gaussian, this integral can be computed. Okay, there is a Gaussian term you can pull out, and the error is controllable. Okay, this is controllable only in some window, but okay, outside this window, in turn we can use the properties of Sn. It is an n-fold convolution of actually quite nice already random variable psi of xi, and we know that farther away, like outside this window, it's you know that okay, for a smooth distribution, for a distribution with a smooth density, the characteristic function goes to 0. This is Riemann-Lebesgue theorem for at infinity, at the tails of the, I mean, far from 0, the characteristic function tends to 0 if this is if the distribution has nice smooth density, let's say. And here it's the case for Sn, but you have to quantify it, and you can do it using okay, it's the underlying distribution like psi of xi, which are the terms of this normalized sum, is nice enough to have a control on the characteristic function, how smallish it is outside this window. So in a sense, outside of this window, this is okay. This is another story, but it's somewhat simpler. Okay, so I thank you very much for your attention, and okay, I guess that I showed you a little bit of the flavor of the proof itself as well. Okay, so thank you very much.
Okay, so thank you very much for the presentation, Pawel. So if anybody has any question, you can just unmute yourself and ask your question to Pawel. No? Okay, so I have one question. What everything you did, Pawel, was for a general Young function, right?
Yes, yes.
Are some of the results improved when you have some more assumptions on your function, like some to convexity or something like that? Like, is in that case possible to extend the interval that was on that set where you could apply Orlicz and Millman?
Yeah, I don't think that any assumption of this kind would help a lot. This kind of assumptions could maybe help to quantify more precisely the dependence of constant and so on and so on. The dependence of constants that are hiding in this O, for example, if we want to know it more exactly, because here it's somewhat implicit. The issue that I was that of the proof, the step of the proof which deals with the characteristic function of Fn outside of this window. Okay, it's somewhat easy technical, but here the quantitative bounds depends on regularity of psi. So yeah, these kind of assumptions could be useful to quantify more explicitly the error in the approximation. but I don't think that applicability of the approximation itself could be enlarged. Here we are sort of in the CLT regime all the time. We haven't pushed it further, but it's probably possible to push it further, namely to enlarge this window from square root of n to, I don't know, n to the power 2/3 or more. There are results in the classical probability on the deviations, estimates for the deviations which are outside the central limit theorem regime. Actually, these are between central limit and large deviations. And I think it's possible to take some tools from these methods and to apply them here with some twists as we already did. Okay, maybe these are not necessary, and maybe some results from the classical probability from book of Petrov can be applied directly. But okay, even with this book at hand, we couldn't find the exact statement. We had to do several twists, but we are pretty sure that if one works hard, one can push it further. But then the methods, even in the classical setting, in the that enlarges CLT regime, in the setting of classical probability, okay, these results are much more involved than just Berry-Essen. These are more technical. It's in the book of Petrov and works of Petrov and his collaborators. These results on deviations of normalized sum within the regime which is larger than CLT. So they provide quite precise asymptotics, which are asymptotics more precise, I mean, at least as precise as here, which are more precise than the asymptotics in classical large deviations, where you have asymptotics on the log scale. Here, this is really precise asymptotics. You have this 1/square root of n, for example, right? So I think that you have to work harder and to see what Petrov and his collaborators, how they did achieve the estimates for the deviations of Sn in the regime which is larger than CLT.
Okay, thank you. Are there any other questions? No? Okay, then if not, we thank you again, although you cannot hear us.
Okay, thank you very much.
Thanks for the talk. And okay, I'll stop.